All right. Welcome back to the interactive sessions of the course Viscous Fluid Flow. Today we proceed with the with eight contents. So quickly, I will basically recapitulate what we saw in the previous week, and then we'll proceed with the doubts and suggestions and questions, and then we'll proceed with this week's contents. So in the previous week, we basically looked at the creeping flow equations, which where we invoke the assumption that the Reynolds number basically goes to zero, and we non-dimensionalize this. Basically, these are the things that we did, and then we saw that eventually in the limit when Reynolds number goes to zero, we end up getting the two linear sets of equation. One, the continuity equation, which is of course valid for an incompressible flow, and the other is basically the fact that the pressure gradient so the gradient of pressure is basically balanced by the viscous forces, which in Newtonian media reduces to the Laplacian of the velocity field. So these are the creeping flow equations that we saw, and then we saw that these equations are indeed linear. So now we can basically use something which is called the method of superposition, where we can use the fact that the equations are linear, and then as a consequence of those linearities, we can now simplify our problem into smaller problems and then connect the bits to get the solution that we desired for. And also we saw that because of the linearity, we saw that we saw two or three examples. For instance, the drag on the objects, which are basically mirror image of each other, when immersed in a fluid which Reynolds number basically goes to zero, is basically the same. So the drag force on the object A and the object B is basically the same, and this is again related to the fact that the governing equations are linear, so we end up actually getting the same magnitude of the drag force. And we also discussed that the idea of the drag force, or idea of the inequalities in the drag force on objects A and B, stems to the fact that inertia is not present, and when inertia is present, the drag force will not be equal. So this was the basic idea, and then we again saw that on account of the linearity, so a complex problem, for instance, a rotating sphere subjected to a linear shear flow, can be decomposed into three simpler problems. And the idea was to evaluate the lift force on this sphere. And we saw that by decomposing the entire problem into three simpler problems, the individual lift forces were zero. And on account of the fact that the governing equations are linear, we said that the lift on the entire system is nothing but the linear superposition of the lift forces of these three systems, that is A, B, and C. And we saw that since individually the lift force was zero, the overall lift of this system, that is a rotating sphere, which is rotating with an angular velocity omega, subjected to a shear flow, is zero, basically. And this again is a consequence of the linearity of the creeping flow equations. Lastly, we also saw that a sphere, when immersed in a bounded parabolic flow, or itself when a sphere is immersed in an unbounded parabolic flow, it won't suffer any lateral migration in the absence of any inertial forces. So this was something that we saw, and we ended our discussion by discussing the spherical coordinate system, because as I said, today we will be solving a system where, so we'll be solving a motion of a sphere that is subjected in a background parabolic flow, and we will heavily use the spherical coordinate system. And this was the idea that so in the last class we briefly discussed what the spherical coordinate system would look like, and more importantly we discussed something which is known as an axisymmetry in spherical coordinate system, which means that the variables are independent of the azimuthal angle phi, and not only the variables, but we also said that the derivatives of the variables and also with the variables are independent of the azimuthal direction, which is basically phi. So if we're speaking about axisymmetry in spherical systems, this means that if u is a variable, it will just be a function of r and the polar angle theta, as we will see. So we will use this axisymmetric principle and in the spherical coordinate system today, as we will see. So yeah, so this was something that we did in the previous week. If you have any doubts or some suggestions or any comments, you can speak out, or you can type in your chat box, or you can later on post it in the discussion forum of the group. We will be happy to address them. If you don't have any doubt, anyways, we'll stop for 1 or 2 minutes and then we'll begin with this week's contents. and the subsequent things that we are going to discuss today. So I'll stop here for 1 or 2 minutes and then we'll begin by this week's series.
A doubt
Yeah, yeah, go ahead.
regarding the assignment.
Yeah. I'm sorry,
Last
there is a noise that is
assignment,
coming
week
out
7
at your
assignment.
end. So can you be more clear, please?
I have, uh, can you hear me right now?
I can hear you, but it's very weak. So, anyways, go ahead. I'll try to understand. Go ahead.
Yeah, and the last week in assignment,
Yeah,
second question. Do you have a question?
yeah, yeah. So I have just wait for some time. I will open my assignment here. So, can you let me know which week assignment? The number, week number,
Week 7.
week seven. Okay, just one
Week
second.
7.
Yeah, yeah. Okay, I'll see. Just one second. So just one second. Okay, so it was on laminar boundary layer. Okay. Anyways, go ahead. So the idea is that we are supposed to discuss laminar boundary layer in the next week. But anyway, you can go ahead. I will try to address if I can, or else I'll post it in the group, like whenever I get time. So yeah, just go ahead.
Yeah. In that
Huh.
assignment, the second,
Second question. Yeah. Okay.
the answer is, yeah, the real answer they have given is the third one, third
Okay.
option.
Okay. Yeah. Yeah. I understand that. Yeah. So the question, which of the following boundary condition is not valid for laminar boundary layer flow over a flat plate along x-axis? Okay. Yeah, yes. So they're saying that the correct answer is C. That so at y equal to delta, del square u by del y square is 0. That's what you are saying, right?
Yes, 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 yes.
Okay. I think this is not correct. That is simply because, yeah, okay. Yeah, that's a good point actually. So just so what I will do is I will discuss it here maybe. So although we are supposed to discuss boundary layer in the next class, but anyways, we will try to address this. So they're asking which of the following boundary condition is not valid for laminar boundary layer flow over a flat plate along the x-axis. Okay. So basically this is the plate and then we'll have a boundary layer developing. So if I take this direction as my x direction, then at any particular x, I will basically have my profile something like this. This is the profile. Let's say for the sake of simplicity, I have a third order profile, or maybe let's not quantify the profile, but it's okay. We'll have a profile something like this. And outside of the boundary layer, we know that the viscous forces won't be there. So the velocity field would basically be uniform. Okay. So this means that so the first boundary condition is what? So the first boundary condition, it says that at y equals to delta, u is basically equal to u infinity, which makes sense because the fluid is basically coming with a constant velocity u infinity and it's a flat plate. So at y equal to delta, which is basically this, so this is your boundary layer thickness delta as a function of x, u is u infinity. So this is correct. The second is basically the fact that shear stress is 0, which means, so this is the second. The second option is at y equal to delta, del u by del y is 0. That is simply because the shear stress at y equal to delta is essentially 0, which means shear stress is mu times, uh, you can simplify it as just du by dy because u is just a function of y or you cannot write du by dy, it's okay. You can just write it as del u by del y at y equal to delta is basically 0. Okay, which means that del u by del y at y equal to delta is 0 because your viscosity can't be equal to 0. The third option, as they're saying, is that at y equal to delta, del square u by del y square is 0. This may not be true. See, I'll tell you why. See, this is not necessarily true. Okay, it's the second option stems from the fact that if del, so the second option is basically the fact that the CA stress is 0, and if you are writing CA stress, so yeah, so basically, yeah, so the, okay, so basically the CA stress as y equal to delta is 0. This is the more fundamental principle, and you are writing the CA stress as just del u by del y times del. So the CA stress is del u by del y plus there should be at least del v by del x, but you are equating del v by del x equal to 0. Okay, so then you can write that del u by del y is approximately equal to 0 at y equal to delta, but its second derivative may not be equal to 0. See, you can just think of something like this. So let's say you are having a third order velocity profile. Okay, so basically a third order velocity profile looks it looks something like this. So can you tell me, so u as a function of y by delta of a third order profile is nothing but, I think, something like this. Okay, minus half y by delta cube. Is this correct for a third order profile? Can you let me know? Uh, so so Jose, is this correct? So is this third order profile correct? Because I want to check that is this is this boundary condition satisfied or not. So this is indeed satisfied for a third order profile, because if you investigate del u by del y here, this would be what? It will be 3 by 2 into 1 by delta minus, it would be 3 by 2 into y by delta squared, if I'm not wrong. Yes. And now if you just investigate at y equal to delta, if you invoke this, this becomes what? This becomes just 3 by 2 delta minus 3 by 2. Uh, did I make any mistake here? Did I make any mistake? So this is okay. This is 3 by 2 y by delta squared, maybe. 1 second. So, so what would be del u by del y here? Let's check it out. So, so this would be 1 second. Can you let me know what would be del u by del y here? Just 1 second. Okay, so I think when you do del u by del y, there would be this 1 by delta into del u. So basically, you need to do this. Okay, and I think this would be 1 by delta into del u by del y. Just 1 second, I'm just checking it out. This would be 3 by 2 delta into 1 by delta. Oh, sorry. This delta would go into the. Okay, I got it. Yeah, so basically what you need to do is you need to, so this u is basically a function of y by delta. Okay, so from here, if you want to evaluate del u by del y, okay, then there would be a delta that is coming out. So it would be delta times del u by del of y by delta. Okay, and then it would be something like this. It would be delta times 3 by 2 into 1 by delta minus half 3 by 2 y by delta. Uh, sorry, what would this be? This would be half of delta cube 1 by delta cube into 3y squared basically. And then at y equal to delta, okay, this term, okay, this delta won't be there because you are doing this y by delta cube. So this would be so basically you can see that at y equal to delta, this term would basically go out to be equal to 0. Okay, it would be 3 by 2 into 1 by delta minus 3 by 2 into 1 by delta. It's okay. So this means this term is 0, but I don't think so that if you now evaluate the second derivative is what? It is just del square u by del y squared. Okay. So the second derivative is basically it's basically what it is. So del u by del y is this. Okay, so del square u by del y square would be what? It is half of delta cube into 6y basically. So this is not equal to 0, right? So can you see? Did you understand? Jose, did you understand that? See, it's just that
The
at
answer
y.
is none in the question.
Yeah, that's why the second. Yeah, that's what I'm saying. That the second
Hello,
boundary condition that it does not hold good. So as you
can you
can see,
hear me?
this is a typical third order velocity profile that you get. Okay, for a boundary layer, if you are using this boundary condition, and then you have validated that the second derivative with respect to y is not zero, basically.
But in the answer, it is correct. They told that the fourth option, none.
Yeah. Okay. So is not satisfied in the fraction. So they have said that the first three options are correct. That's what you are saying, right?
Yeah. The question is which is not valid.
Okay, and
In
they have
that
said
they
it
told
is
none.
none.
Yes.
All right. All
So
right.
second question, week 7.
Okay. Actually, in deriving the boundary layer, I mean, in deriving the velocity profile such as this, or any first order on a sine velocity profile, we don't use the second boundary condition. So anyway, I'll look into it. It just so I'm thinking that if so this means that if del u by del y is 0, would it mean that del square u by del y square is also 0? Okay, anyways, I will look into it. Is it fine? Like, I'll look into it basically, and I'll either post it in the group or I'll discuss it in the next class, basically. Is it fine?
Uh, it is fine. In which where will you post in discussion forum?
Yeah, I'll post it in discussion forum, and also I'll discuss this thing in the next class when we'll meet. Okay, when we'll basically do the
Oh,
boundary layer theory. Is it fine?
yes, it is fine. It
So
is
I'm
fine.
just thinking,
Actually,
sir.
uh,
Yeah, let me know.
I have actually one more very small doubt. Actually, very
Yeah.
small doubt
Yeah, but before going to that, I'm
in
just
week
thinking,
5 assignment.
okay, just one second. Well, just one second. I'm just thinking that
Okay.
before going to this, I'm just thinking that so this profile is correct, right? It's a third order profile. It seems correct because let's just think about it because it's a very trivial question and yet like
Actually, I have a doubt regarding that also.
okay. So
From
what's the
where
what's
did
the
you get
doubt?
that equation? It's a Blasius equation, or
So this doesn't comes
from
from
where
the
did you
Blasius
got that
equation,
equation?
okay? This is basically an approximated velocity profile. So the idea is, yeah, I'll tell you the idea. Anyways, I'll tell you the idea. Uh, so since you have just asked it, so I'll let you know. So the idea is in momentum integral approach. So I think you're familiar with the momentum integral approach, right? Von Karman momentum integral approach. So anyways, the idea is that
Okay.
you know that the velocity profile of a boundary layer is not exactly solvable. So the exact equations of the boundary layer profile is obtained from the Blasius solution, that similarity approach and all those things. Okay, but that is indeed a very very cumbersome and a complicated approach. So what people do is they approximate the velocity profile as something like this. Okay, I'll just show you. So what they do is something like this. So u infinity they consider as some a naught plus some a1 times of y by delta, okay, plus some a2 times of y by delta squared plus a3 times of y by delta cube, okay. And then the constants, so this is the approximation that people take, okay. And the constants a0, a1, a2 and a3 are derived, and so these are obtained from the boundary conditions. So for instance, the first boundary condition that people use it at let's say y. So this is your x, meaning this is your y. So at y equals to 0, one thing that we are sure of is that the fluid will, so the x direction velocity would be 0. This is due to the no slip boundary condition. Okay, so this means that u at let's say y equal to 0 is 0, which means from here you can directly say that a naught becomes equals to 0. Okay, if you invoke this boundary condition, so this means that a naught is equals to 0. The second boundary condition people use is that at y equal to delta, okay, u at y equal to delta is basically u infinity. This is again because of the fact that at y equal to delta, the fluid velocity is nothing but the first stream velocity. Okay. So similarly, you can get a constant out of this, and the third constant, and So we have 4 unknowns here, right? So we have A0, A1, A2, A3. Okay, so this means that we need 4 boundary conditions to find out the 4 constants, which means that the third condition, what people use it at y equal to delta, since, so what happens at y equal to delta? Since the velocity is basically attaining the free stream velocity, this means that there is no velocity gradient along the cross stream direction, which means that the shear stress tau w at y equals to delta is 0, which I basically said some time ago. Which, so this condition will just give us the fact that del u by del y at y equal to delta is 0. Okay. The fourth condition basically comes out from the fact that, yeah, go on. You want to say something?
Continue.
Yeah,
Please
yeah.
continue.
Yeah, the fourth condition, if we want to evaluate the fourth constant, okay, stems from the fact that if we now apply the momentum equation at the first layer of fluid, which is above the plate, okay, let's apply the momentum equation at the layer of fluid, which is basically above this plate. This will give us the fact that, so what is the momentum equation? It is just u times del u by del x plus v times del u by del y. So this is the flat plate momentum equation that you guys have saw, and this is equal to, so it becomes equal to nu times del square u by del y square. So this is the simplified x momentum equation for a flat plate. Okay, now if this equation is being applied at y equal to 0, this will, so let's see what happens. Okay, this means that u at y equal to 0 is 0. This is 0 because of the no slip. Okay, remember we are applying this equation at y equal to 0. So this term would be basically 0 due to no slip. This term would be 0 due to no penetration. Okay, because fluid cannot just penetrate through this, so this flat plate is basically non-penetrable, so the fluid cannot move inside this plate. So this becomes equal to 0, which means we end up getting this condition. Okay, so we end up getting, del square u by del y square to be equals to 0. Okay, this happens at y equal to 0. If we use these 4 conditions, you can see that you will see that this a2 will go out to be 0, a0 will go out to be 0, a1 will come out to be equal to half, and a3 will come out to be equal to minus 3 by 2. Okay, so that's the idea. How is this obtained? How the velocity profile, how an approximated velocity profile is obtained, basically.
Okay, fine, thank you. Yes, yes.
But I was just thinking that so let's do this and say, can you tell me that so let's just verify this. Okay, let's just verify this. So from here we saw that a naught is equals to 0. Okay, let's use the second boundary condition and see what do we get. So we apply this at y equal to delta, u is u infinity. Okay, so this means u is u infinity by u infinity, and a naught is 0, which means I have a1 into y by delta. So we are evaluating at y equal to delta, which means this should be 1. This term would be 1. Okay, this term would be a2, and this would be a3. Okay, so yeah. So we have a1 plus a2 plus a3. Yeah, so I think this would be this, if I'm not wrong. Okay, this is the second condition. The third condition says that its gradient, so del u by del y at y equal to delta is 0. Let's now evaluate what is del u by del y. So if I evaluate del u by del y, this would be what? So let's evaluate del u by del y. So this would be u infinity into, the first term would go out to be 0, and this would be a1 by delta. Okay, plus this would be what? This would be 2a2 by delta squared into y. Okay, I think this, so this is basically the derivative of this term. So it would be 2a2 by delta squared into y, and this term would be 3a3 by delta cube into y square. Okay, should be plus 3a3 by delta cube into y squared, and we are evaluating this at where? We are evaluating this at y equal to delta. Okay, so if I put y equal to delta here, so what will we get? So this is 0 basically, and this becomes a1 by delta plus this would be a2 2a2 by, so we're evaluating at y equal to delta, so this would be delta plus this would be what? This would be 3a3 by delta precisely. So delta is non-zero, so this will get cancelled, which means we end up getting one equation, a1 plus 2a2 plus 3a3 equals to 0. Okay, this is the second, so this is the third boundary condition. And the fourth boundary condition is, what? The fourth boundary condition is that its second derivative is basically 0 at y equals to 0. Okay, so this boundary condition is true because it is obtained from this equation. So let's evaluate the second derivative and see what do we get. So the second derivative is nothing but del square u by del y square. Okay, this means what do we get? We get u infinity times of what, 2a2 by delta squared plus it would be 6a3 by delta cube into y precisely. Okay, and this evaluated at y equal to 0 is 0, which means I have a2 to be equal to 0. Okay, this means a2 is equal to 0. Okay, this is the fourth boundary condition. So this means this a2 is basically 0. Okay, this a2 is 0, which means I now need to solve two unknowns. Okay, so what are the two unknowns? Unknowns are a1 plus a3 is 1 and a1 plus 3a3 basically. 3a3 is basically equal to 0. Okay, so now if I just add this, what do we have? I have so yeah, so let's not add it, let's subtract one from the other. So if I subtract one from the other, let's subtract 2 from 1, then I have 2a3 is equal to 1, which means a3 so what we are doing is we are subtracting this. So we are subtracting this from this, so this becomes -1 in fact, because we are subtracting this equation from this equation. Okay, which means a3 becomes equal to -half. Okay, a3 becomes equal to -half, and if you put this in equation 1, a1 is nothing but 3 by 2. I mean, you are putting this is here, so you are putting a3 equal to -half here. Okay, which means using these boundary conditions, what you get is the velocity profile u by u infinity is something like this. So u by u infinity is then becomes, so see, we considered u by u infinity as a series solution, right? So this becomes, so a1 is what? A1 is 3 by 2, so this becomes 3 by 2. Oops, 3 by 2 into y by delta minus half y by delta cube, because a3 came out to be equal to -half because of this. All right, now let's check the validity of the question. Now let's check the validity of option C in question number in assignment 7. Okay, so let's now evaluate so let's now evaluate what is del square u by del y square at y equal to delta. Okay, from this obtained expression. So the first derivative would be what? Del u by del y would be u infinity times 3 by 2 delta minus it would be what? It would be 2 would get cancelled, so it would be y by delta squared if I'm not wrong. Okay, just let me know if I'm wrong. So this would be y square, y, so 2 and 2 will get cancelled and there will be delta squared. Yeah, and now let's evaluate what is del square u by del y squared. Okay, so this would be minus u infinity. Okay, this would be what? This would be minus u infinity by delta squared, right? So this is what del square u by del y squared turn out to be, right? So this means that at y equal to delta, is this correct?
Is it y cube
Sorry, I
or what?
think, yeah.
Half into y by delta whole cube? U by
Okay,
u
okay, yeah,
infinity
yeah,
is
yeah.
the
Sorry, sorry, yeah, yeah. I'm sorry, yeah. This would be cube actually. Thank you. And then this would be what? So del u by del y would then be, okay, then this would be, I'm sorry for that. This would be, so 1 by 2 delta squared, delta cube would be there, into, this would be 3y squared. So it would be 3y squared to be precise. Okay, which means, let's simplify this. This would be u infinity into 3 by 2 delta minus 3 by 2 into y square by delta cube. I hope this is fine. Okay, now if you evaluate del square u by del y squared, this would be what? U infinity times this minus 3 by 2 delta cube would be there unaltered, and this would be 2y. Okay, which means now if you substitute y equal to delta, this del square u by del y square would just come out to be u infinity times minus u infinity times 3 by 2 delta q into 2 delta. So this is not equal to 0, right? For a finite value of delta. This is just
Yes.
minus 3 u infinity by delta basically. Okay.
Yes.
So this is non-zero, right? I hope
Yes.
this means that the option C is not correct actually. So, but they have said that the option D is the correct answer for question number 2. That's what you're saying, right?
Yes, we are saying it none is the answer of the second question.
Achha, okay. So IUC, did you do these questions? Did you do this? Do you also end up getting the same doubt for this question, or you marked it right?
Yes, yes. I marked it option C. Correct
Okay,
option is
okay,
B.
okay, okay. So I think this question is not okay. So what I would do it, I would mail the instructor about this question because the correct answer for question number 2 should be option C. Anyways, I'll mail the instructor and let's see whatever will be the response. I will post it in the discussion forum and also in the next class. Okay.
Okay, thank you, sir.
Yeah.
One more doubt.
Yeah.
Can I
Please go
have?
ahead. Yeah. Sure. Please go ahead.
I had already posted in discussion forum, but I didn't get any answer, so I am asking
Okay.
again.
Yeah. Sure.
In week 5 assignment,
Okay. Week 5. Please start. Week 5.
question
Yeah.
number
Okay.
2.
Question number 2. Okay. Let's see. Hold on. Okay.
Actually, they are asking about YZ plane,
Uh-huh.
which is the maximum flow velocity.
Okay.
Actually, it is when Z is equal to 0 and Y is equal to A by 2 root 3.
Okay. So you're saying the correct answer should be Z
C.
equal correct answer should be C. Okay.
Yes.
So they have marked
But
you.
the
Yeah.
correct answer given is D.
Correct answer. Okay. I see. So
The thing
this
is that
I
it is
actually need to solve it by myself. I haven't solved this question yet. We have discussed similar question to it, but I actually solved. I didn't solve this. So was it solved in the week's class basically?
yes, that is shown in that equilateral triangular tract video. In
Okay.
that they had written like 0 comma a by 2 root 3, but I thought is that when we express the coordinates, we express it like x comma y comma z, or if
Yes.
y and z is there, we will be expressing only y comma z.
Y comma Z. Yeah. Correct. Okay.
But
So
in the
there.
video also it is wrong actually.
All right.
In the video
Okay.
also they had shown like 0 comma a by 2 root 3.
Okay. Okay. Anyways, so I will post. Maybe I'll post the instructor. I'll let him know like these are the doubts on this. See, I have not solved this question number 2 by myself, so maybe I need to solve it once and then I can just come out with this with the conclusion on this answer. But I will let the professor know about this. Is it fine?
Yes,
So
sir.
this is
Yeah,
question.
And
even
Yeah.
I have one doubt. In same assignment, fifth question number 1 actually.
Okay. Same
If
assignment
this
question. Yeah. Go ahead.
uh, if that center is at geometric center, so boundary condition should be at a by 2 comma b by 2, like something like that order, right?
Okay. Hmm.
So option should correct option should be none, but they have given some other.
They have given some other. Okay. Anyways, okay. Thank you for that. I will ask maybe the professor on this. So this question 2 and 1, of course, question 2 and 1, okay, of assignment number 5. Okay, this also needs to be clarified. And
then in that also one more doubt is there. Question
yeah,
assignment 5.
go ahead.
That seventh question.
Seventh question. Okay.
Seventh question they have given like dou p by dou z is 0.4.
Okay.
Uh, Is it dopey by dou set itself? In the equation, it is. I think it's not dopey by dou set.
So this is okay. It is to an equilateral. It's the same equilateral triangular duct. Okay.
Yes, yes. So that's a triangular duct. Let's take that page. One
So
second,
Dou p by
please.
dou x, it is h.
Yes, it should be dopey by dou x.
okay, yeah, that is because the axial direction is the x direction, right? So if you are looking in the velocity in the yz plane, then the pressure gradient should be in the axial direction, right? So it has to be dou p by dou x. Yeah, that's a mistake. I mean, I think that's a so. Is that so? Do you have some other doubts related to this, or the fact that the j should be replaced by x? That is that what you're saying?
Yeah, so I actually it is dopey by dou set, so I didn't use this value. So my
Okay.
answer is different, and the answer got wrong.
Oh, okay, 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 okay,
There is another equation also we can use without this dopey by dou set actually. They
okay.
are asking about pressure drop. So I think you can find it from other equations. So I think
All right. Okay, so this has to be so question number 7. This also has to be minus dp by so this z should be equal to x. Okay, that's what it should be. This not z, it should be x because since the yz plane is this, then basically the axis which is into or away from the plane is uh, the x-axis. Okay. So anyway, yeah, that's okay. I'll discuss with it, and maybe since if these questions are wrong, then like it can be like so we could come around at a conclusion that we can give marks to like all the answers that people have submitted. So it would be possible.
okay, so thank you.
Yeah. So anything else?
No, sir, only this.
Okay. Okay, all right. So I will try to contact like the instructor on this. This is maybe I'll just write it. So this is of assignment. So
Week 7. Week
this is
7
yeah.
assignment.
So this is assignment 7. Question number is what?
2, 2.
Question number 2. Okay, so question number 2 that the correct answer should be option C. Basically, correct answer should be C. So we will see, but they have written it as D. Okay, so we will try to clarify this. All right. Okay. Thank you. So yeah, I'll try to like connect him and try to get these things clarified. Okay. In the next class, and whatever is the update, I will post it in the discussion forum of the group. All right.
Okay.
So okay. So then let's begin with today's. Let's begin with today's discussions. So basically, in the last class, as I have said, we looked into the equations of creeping flow. Uh, where is it? Yeah, so we looked into, so I showed this. So we looked into the creeping flow equations, and then we saw the principles and the consequences of non-linearity. So now, to in this, so I today, and of course, like if it is not possible for us to finish it today, we will see it in tomorrow, and then later on we'll proceed with the boundary layer theory once this is finished. Okay, so we will see the stream function approach. I think the glimpse of this you have seen while you try to solve the lubrication problem, or like even if you didn't solve the lubrication problem, I think you when you solve the creeping flow motion of a sphere in an unbounded uniform flow, or the force or the drag force on a sphere in an unbounded uniform flow, I think you guys need to follow the stream function approach because it's a axisymmetric problem. So basically, the only resort we have is the stream function that we need to define. Okay, so we will quickly get a glimpse of the stream function approach, and then today we will solve a similar problem, but now we will solve the motion of a sphere in an unbounded Bragg parabolic flow. Okay, so in the week's class you have solved the drag force on a sphere which is subjected to a uniform flow, that if you are holding a sphere stationary in a uniform flow which is moving at u, what is the drag force that this sphere would experience. Okay, this is something that you have solved. This is that famous Stokes drag force that you basically do. Okay, here what we will do is, instead of like calculating the drag force, we will allow the sphere to move. Okay, and then what we'll do is we'll try to calculate what will be the velocity of the sphere if the external forcing that is being generated by the background flow balances the drag force. Okay, so the idea is that if we do not allow the sphere to be held in a particular place and we subject this sphere to move, then the external force that this background parabolic flow would exert on the sphere would basically be balanced by the drag force. So if these two forces are balanced, okay, then the sphere basically moves with a continuous yet unknown velocity in the z direction, of course, and our objective is to evaluate that velocity. So I hope this is clear. As we will proceed this problem, things will be much more clarified. And for this analysis, we will basically use the stream function approach and the spherical coordinate. Okay, something that we saw, the glimpse of something that we saw it in the last week. So let's begin. Uh, let's begin and maybe from here. So we saw that the creeping flow equations basically ended up something like this. So it was the gradient of pressure plus del square v equal to 0 and the divergence of velocity equals to 0. Okay, so now can you guys tell me that but before that, let's do one thing. So if I if I take a curl of, let's say this is equation 1a and this is equation 1b, and if I take a curl of equation 1a, so what I will do is I'll do 1a and I'll just take a curl on this equation, which means what do I get? So I get minus curl of grad p plus curl of del square v, and this is equal to 0. Okay, so can you tell me what would be this? So the idea is I'm just considering the creeping flow equations. This is the, so 1a is the momentum equation, 1b is the continuity equation. We will look into the continuity equation some like later on. But if I take a curl of the momentum equation on both sides, I end up getting something like this. So can you tell me what is curl of gradient of pressure, where pressure is any scalar quantity? Can you tell me?
0.
Yeah, exactly. So curl of grad p is 0, which means and of course there is no body force into the problem, which means our equation basically simplifies to curl of del square v is equal to 0. Okay, now can you guys tell me how is velocity basically related to the stream function in vector form? I mean, I'm not asking you in component wise that u is del psi by del y and v is minus del psi by del x. This form of the stream function is actually obtained from the more generalized relation between the velocity field and the stream function vector. Okay, so I'm asking that what's the relation between velocity field and the stream function in any generalized coordinate system? That's what I'm asking. So do you want to give it a try, or like I'll state that here? See, the idea is that we want to, so these are two equations, right? And these are PDEs, of course. So the idea is instead of solving two PDEs, our objective is to convert the two system of equations into one higher order system of equation. Okay, and that's why we are using stream function. And I'll just state the answer to the velocity. But before that, is stream function a vector or a scalar? So do you have any comments on that? So or if I say that stream function is actually a vector, so is that statement true or false? Can you tell me? So so again, if the question is not clear, I'm just asking a simple question, that is the stream function that we used. Okay, the stream function that we use, and we all know that psi is null.
Scalar.
Yeah, yeah, stream function is a scalar. That's what you said, right?
Yes.
That actually is not. so trivial, so it's not actually a scalar quantity, and I'll show you actually why. The stream function is not actually a scalar, and in fact the stream function is a vector. It's actually a vector, and what we actually write is actually the magnitude of the stream function as psi. Okay, so basically that's what I will just show you. So basically the velocity field is related to the stream function vector as something like this. So it is just it is just curl of psi. Okay, at least in the Cartesian coordinate system. So this means that if this is a vector and if I'm taking a curl, this has to be a vector, right? So it's obvious, right? Because we cannot take a curl of a scalar quantity. So is this correct or not? So did I make sense or not? That had this been a scalar, then you cannot relate velocity with stream function as like this, right? So okay, so I think it will be clarified. Now, what we write is basically something like this. So we just write that curl of this stream function vector, we just write it as psi times Ez. And this has to be in the Ez direction if we are trying to solve a planar problem in the xy plane. And we will see shortly why this has to be. Okay. So it is so now what you guys know, or what you guys generally do is that the relations that we use, that u is del psi by del y as v is minus del psi by del x, is basically applied on this magnitude of the stream function vector. Okay, and we will see shortly. So let's evaluate this quantity. Okay, let's evaluate this quantity and see what do we get. So if I evaluate curl of psi, so I think you guys know how you guys know the standard procedure of evaluating curl. So this would be something like this. So it is just ex, ey, ez times curl would basically give us del del x, del y, and del z, and psi has a component in the z direction, so that's why it would be psi. Okay, so now if you evaluate, what will you get? You will just get del psi by del y ex minus del psi by del x ey, and there won't be any z component. So now what I am doing is I am just writing, so as I said, this is the velocity field, so this means this is our velocity field. Okay, so now if I now compare it, so we know that velocity field can be written as u times this minus v times this. So if I now compare it, this means I get that u is basically equal to del psi by del y, and v is nothing but, this would be plus. Okay, and this v is nothing but del psi by del minus of del psi by del x. Okay, so from here u is nothing but, sorry. So from here u is nothing but del psi by del y, and v is nothing but minus del psi by del x. Okay, so so I think you guys are just familiar with this relation, but actually stream function vector has its own direction in the ez direction if we are trying to solve it in a planar system in the xy plane. Okay. All right, so I hope this is clear. So yeah, so this is something that I wish to say. So now let's move ahead. So what I say is that, so I just have, so what do I have? I have, sorry, what do I have? I have so I have curl of del square v equal to 0, and I said that my velocity is basically this thing, which is basically the curl of the stream function vector. Okay, so I'll just substitute it here, which means this becomes curl of del square v is nothing but curl of psi bar, and this is equals to 0. Okay, and if I now rearrange, so let's now rearrange this, so I can write it as del square times curl of psi bar. Okay, so now let's do one thing. So there is a property, so curl of any vector a, this can be written as, so this can be written as gradient of divergence of a, okay, minus, oops, del square of a. Okay, and if I apply this if I apply this property here, so what would this become? So this becomes del square into, this should become gradient of divergence of the stream function minus del square psi. Okay, this is equal to 0. Now, can you tell me what is this? And this, of course, is a vector. So, can you tell me what is this? For an incompressible flow, see, we have not utilized one more equation, which is basically the continuity equation. Okay. So, can you tell me what is this? What this quantity would become? See, you can show that if your flow field is incompressible, then it means that divergence of velocity in 0. And if you use the velocity stream function relation, you can similarly show that the divergence, your stream function is also solenoidal, which means that the divergence of your stream function is also 0. So this means we'll just end up getting minus del square of del square psi bar equals to 0, and this would just be del power 4 psi bar equals to 0. So this is actually your actual equation which the stream function vector satisfies. Okay, so this is the equation that psi bar satisfies, which is essentially a fourth order equation, as you can see. Okay, now if we use this relation that u is del psi by del x and v is nothing but minus del psi by del y, then you can say that the magnitude of the stream function essentially satisfies, magnitude of the stream function psi essentially will satisfy del to the power 4 psi equal to 0. And I think this is something that you are more familiarized with. Okay. All right. So I hope this is clear. Do you have any doubts? So I'll stop here for 1 or 2 minutes. If you have any doubts, you can just ask me. But this concept has to be clear, that how velocity and stream function are related. And essentially this stream function is not, so it's not a generalized scalar. We essentially deal with the magnitude of the stream function, knowing that its direction is fixed along a particular its direction is fixed along a particular vector. That's the idea. All right. If you have any doubts, you can yeah. But before that, the stream function. So the stream function satisfies this equation. Okay, where del square is nothing but the Laplacian operator, which is basically this thing. All right. I would quickly like draw comparison of this with the spherical coordinate system. So what I have said is that since, so this is true, okay, for a Cartesian system, in the same spirit, it can be shown that in spherical coordinates, okay, the stream function essentially satisfies E4 psi equals to 0, where E4 is a similar operator as the del 4, as this del 4. Okay, it's similar, only that we are now moving on from a Cartesian coordinate into a spherical coordinate, and this E square in spherical coordinate looks something like this. So it is del R2. Okay, so it's del 2 by del R2 plus 1 minus eta squared by R squared into del 2 by del eta 2. Okay, where this eta that you saw here is nothing but the cosine of the polar angle. Okay, so this is how this E square looks in a spherical coordinate system. And the relationship between the velocity and the stream function is similar in spherical coordinate. It is just the curl, as we saw, it is just the curl of psi by r times square root of 1 minus eta square into E phi hat. So this is the relation. Okay, this is how the stream function, so this is the equation that the stream function satisfies in spherical coordinate system, where E square is basically this. We have introduced a new variable eta in place of theta, where eta is basically the cos theta. Okay, so the idea is basically to simplify the equations that we will be solving. We will see that shortly. But generally in spherical coordinate, instead of using theta, we generally transform it into the eta variable. So this means, can you tell me if theta, as you know, varies from 0 to pi, eta varies from what? Can you tell me? So you all know that in spherical coordinates, r varies from 1 to infinity, or r should vary from 0 to infinity. The azimuthal angle phi varies from 0 to 2 pi. Okay, and the polar angle varies from 0 to pi. So if this, then what is the range, or what is the range of this, or in fact I should say what is the domain of this eta variable? Can you tell me?
-1 to
1
1.
to minus
Yeah,
1.
exactly. It just varies from -1 to 1. Exactly. That's true. Okay, so we will briefly stop here for some time, and if you have any doubts, you can ask me. Again, the idea is, so if you ask me why are we doing this, the idea is that instead of solving the two couple PDEs, that is the basically the momentum equation, which is nothing but the gradient of pressure plus del square V, and the fact that divergence of velocity is equal to 0, we are coupling and transforming these two equations into a single biharmonic. So this operator is called as a biharmonic operator. So we are transforming this into a single biharmonic operator of psi, where this psi is nothing but a magnitude of the stream function vector, and the velocity is related to this psi as something like this. Okay, so we all know that velocity is nothing but the curl of the stream function vector. And in spherical coordinate, this basically looks something like this. Okay. So this means, as I have already said, you can use, so the bottom line of this analysis is that this stream function approach, okay, this stream function approach can be used for 2D oblique axisymmetric problems. Okay, this is important. So that's one limitation of the stream function approach, is that you can use, so by the techniques that we know, we can use this stream function. So although stream function vector is a vector, and it can be defined in any 3D space, the I would say the manner of using this stream function vector into finding solutions by using this biharmonic equation is the fact that your domain, or your physical paradigm, should be either it's 2D or it should be axisymmetric. Okay, which basically, so you know what is axisymmetric, so you know what is cylindrical axisymmetry, what is spherical axisymmetry, that we have discussed it. So the idea is that this can only be used when your problem is two-dimensional in Cartesian system, or it is axisymmetric in spherical or cylindrical coordinate system. Okay, so this is the idea. So this is the idea, and we will, so with this, so I'll stop here for 1 or 2 minutes. If everything is clear, we will then proceed into solving the problem that I have stated. So it's the motion of a sphere, okay, that is subjected to a background parabolic flow, which is, so that's what I was saying, that there is a sphere which is now subjected to a background flow. And if I say that I don't seek to hold the sphere stationary, and I wish that the sphere would now move, meaning that the external force that this parabolic flow would exert on the sphere, okay, which will be in this direction, is balanced by the drag force. And if these two forces are balanced, that if Fe plus F drag is equal to 0, this means that the sphere would now move with a constant velocity. And our idea is we will use this constraint that the sphere, that the hydrodynamic net force on the sphere is equal to 0, and this would give us, so this constraint would essentially spit out what the velocity should be. So that's the idea. Okay, so initially we will treat this velocity as an unknown, and we will use the hydrodynamic force free condition. This means that the summation of the drag force plus the external force on the sphere is 0, would ultimately give us what the constant velocity. So what is the constant velocity with which the sphere would move subjected to this parabolic flow? So that's the idea, and that's the question that we will try to solve. I'll wait here for 1 or 2 minutes. I'll just come in 1 minute. If you have any doubts, you can ask me, or we'll begin by a better understanding of this problem, and then we will start off with the solution procedure. I'll just come in a couple of minutes.
For this final exam also similar type of assignment questions. Do you know anything about that, Ayush?
Yeah, yeah. Final exam, I think multiple choice only will come.
Similar to this type of problems in
Yeah,
assignment.
yeah, multiple choice and numerical means answer filling type.
Do you have any Do you have any this previous papers or anything like that?
No, I am also giving first time only. I don't have.
All right, guys.
Can you have the
Yeah.
previous type questions or sample questions, or is it similar to this?
Uh, can
The
you just
final
repeat?
exam, final exam,
Yeah, yeah. I, you are not just
not
that
audible,
audible. Can you just
not
repeat
audible.
once again? Yeah.
Your mic is off.
Sorry, I was just telling that you are not audible. So can you repeat your question?
Previous exam or sample questions of final exams, will we get that?
Actually, to this end, I don't have these questions with me, but I don't know how the final exam questions look like. But I think it would be similar to, so it should be similar to the questions that you solved as a part of your assignment. Okay, it's not that big and not like, yeah, go ahead.
No, no, no. Okay, 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 fine.
So I don't have the questions of the final exams with me, so it is set by the NPTEL office. So that I don't have. But uh, like as per my understanding of these exams, so it would be similar to the, so the level is similar to the ones that you solve for the assignments in so it's the same as the assignments that you do every week, basically.
Okay, fine, fine. So we have to remember a lot of formulas.
Yeah, I understand. So the thing is, yeah, I
Okay.
understand that. I understand that. The thing is like, see, then there is one thing that you cannot just. So, for instance, if you wish to, if you wish to evaluate something from that by applying a Navier-Stokes equation in cylindrical coordinates, then there is no point remembering the Navier-Stokes equation in cylindrical coordinate, right? Because that's too big, right?
Okay, okay, fine.
So
Yes.
I think at that instance, or in that case, you would be given with the prerequisites, basically, that this is the Navier-Stokes equation in z direction, in the r direction, or in the theta direction, basically. So that would be given. Now there are certain things that you can I mean that you basically need to know. For instance, like if I ask you that what is the relation between the average velocity and the maximum velocity of a plane fluid flow? So that's just 3/2, right? So that
Yes,
things
yes.
like you know, basically, or you should know, because like these are used multiple times. Rather than that, if so, to my understanding, like if you need things which is difficult to remember, difficult to like keep in mind, or there is no point keeping that in mind, because you just need to apply them. So this has to be given with you, like, or with the questions. Okay. So like in the assignments, since so they know that you have seen the lecture series, and they know that like you are taking notes of the formulas and so on and so forth, and you can take help of the net to, like, look into how the basic formulas look like. So that's why they take it for granted that you know this, and they just pose the questions. But this will not be the pattern in the examination, because like examination is a so it's a platform where basically you don't have access to anything else. not even your notes. So I think that's the idea. Okay. But honestly, like I didn't give the exam of this course, so like I don't know basically what's its pattern and what's the like what the template would basically look like, that I don't know like as of now.
Okay.
Yeah.
Thank
Okay.
you.
Yeah. Okay. All right. So we'll begin. So we'll begin by solving this. So the again I said the objective is to hold on. Where did I start? Yeah. Hold on. Okay. So so as I said, the objective is to like evaluate the unknown velocity u with which this sphere, okay, of radius 1. So because this everything that you saw here, these things are just non-dimensional. Okay. So the idea is that so if a non-dimensional sphere, okay, of let's say radius 1, okay, moves in this parabolic flow, okay, then what would be this velocity if I now don't constrain the sphere to remain fixed at a particular location? All right. So the idea is that the only bit of information that we know is that the far field velocity is known. And now if we fix and remember this rho is basically the cylindrical radius, because we are going to use spherical coordinates. So I will use this small r as my spherical radius, and I will use this rho as my cylindrical radius. Okay. And we will use spherical coordinate system as I have said. But the only bit that we know is that the nature of the parabolic flow is known. So basically, in non-dimensional sense, if I want to, so they have given us that the parabolic flow basically looks something like this. So it is just 1 minus rho square Ez. So that is a typical parabolic profile that you can assume. But the question is given to us. Now, if we fix the axis system to be fixed, so the axis is basically fixed at the body center. So it's at the center of mass of the body. This means that the far field flow, by using the concept of relative velocity, would basically be the parabolic flow minus the flow with which the particle would travel, which is basically u. And of course, since this is an axisymmetric problem, there won't be any migration, as I have said. So we have already studied that in the creeping flow limit, a sphere subjected to a background parabolic flow will not suffer any migration. It won't suffer any lateral migration because of the fact that the governing equations are linear and the problem is 4f symmetric. Okay, which means that this u vector is just its magnitude multiplied by Ez, and that's why the far field flow with respect to an axis which is fixed at the particle center looks something like this. So this is given to us. Okay, and this rho is the non-dimensional cylindrical radius, which is basically a dimensional cylindrical radius multiplied by the radius of this parabolic flow, which is basically r, let's say. Okay. So using this information and using the fact that I know that my problem is spherically axisymmetric or it is cylindrically axisymmetric, but we will use spherical coordinate system. And this means that I know that the stream function satisfies this equation, where E square is basically something like this. Okay. The idea is to obtain the complete solution for the stream function and then to obtain the velocity at which the sphere would move if I use the fact that the external forcing is being balanced by the drag force. So I would repeatedly ask that is the problem statement clear or not? Like, can you give me, like, is it clear? It's fine. If it's not clear, please let me know and I'll explain it again. So is it clear?
This rho dash is the radius of small sphere.
Yeah. So this rho dash is basically the non-dimensional cylindrical radius.
Okay.
Okay, and we are just non-dimensional. Oh, sorry. I just said it wrong. So rho is basically the non-dimensional cylindrical radius, and rho dash is the dimensional cylindrical radius. So we are non-dimensionalizing this dimensional cylindrical radius with the radius of the cylinder, basically this capital R, which is, so it's like you can think of that there is a, like, what you say, invisible cylinder. Okay, there is an invisible cylinder which is basically generating this background flow, and that radius of that invisible cylinder is basically r. Okay, and we are using this to non-dimensionalize the cylindrical coordinate system. I mean the cylindrical radius, and hence the non-dimensional cylindrical radius is this dimensional counterpart divided by the characteristic length, which is r. Is it fine?
Yeah.
Okay, so we'll begin we'll begin by the solution. Okay, and let's see how far we can go. So first, like before explaining these things, okay, I would just say that, so what now we need to do? So our objective is, basically to solve this biharmonic equation, which is E4 psi equal to 0. Okay. Now, luckily, the manner in which, so the fact that there is a very famous technique which is known as the method of eigenfunction expansion, okay, which is basically used to obtain the solution of this psi. Okay, but before that, can you tell me now what will psi be a function of? Can you now tell me, if this is a spherically axisymmetric problem, what will psi be a function of? In terms of, so yeah, of course, now we are dealing with cylindrical, we are dealing with spherical systems. So what will psi now be a function of in spherical coordinate system? Yeah, go ahead.
R comma theta.
Yeah, exactly. So it will be a function of r comma eta. Okay. So what people do is, they have, so they use something which is known as the method of eigenfunction expansion. I just write it here. So this is a like standard method. So it's a standard method for solving biharmonic equations, and they use this to solve for an explicit equation for psi of r comma eta. Now, luckily, so this solution is being well tabulated, and this is expressed as a series solution, something like this. Okay. I would lay down the solution, and I would explain to you how this solution come from. I will not explicitly show you how to derive this solution because it's too long. But if you are interested, I will give you a separate note where I will show you how to actually evaluate the solution from this biharmonic equation by using the method of eigenfunction expansion. Okay. But in the interest of time, I will not show you the method, but I just straight away write the solution. So the solution from psi in spherical coordinate system as a function of r comma eta basically looks something like this. So it is summation n equal to 1 to infinity. It's a series solution basically. It becomes a n times r power n plus 3, okay, plus b n times r power n plus 1 plus c n times 2 minus n, okay, plus d n times r power minus n multiplied by, so this is a function of r, this is multiplied by qn of eta, where these qn's are known as the Gegenbaur polynomial. So these are known as the Gegenbaur polynomial. Okay. And these Gegenbaur polynomials are defined from another set of polynomials. So this means that qn of eta is nothing but integration from -1 to eta. So if we integrate the Legendre polynomials Pn of eta as a function of d eta from -1 to any eta, it gives us the Gegenbaur polynomial. Okay. All right. And this is basically the series solution that satisfies this biharmonic equation. So I'll just briefly, so yeah, so now if you ask me that how did you obtain this series solution, so I would say that this is obtained by using this method of eigenfunction expansion, and this is the final result that is obtained by using this eigenfunction expansion thing. Okay, so I just quickly give you an idea how this is used. So basically they define something. So what they do is, in order to solve this biharmonic equation, what they do is they equate that, they said, okay, now I define my psi as something like e square omega. Okay, and then what they do is they substitute this psi into this. Okay, now this will end up into getting two equations. One is that e square omega is basically equal to 0, and e square psi is basically equal to omega. First they use this equation, first they use the first equation, that is e square psi equal to omega, get the answer of that harmonic equation, and then substitute this into the e square omega equal to 0 to obtain the solution of this e power 4 psi equal to 0. So that's the idea. If you have if you are curious to know about the answer or about the methodology how to use eigenfunction expansion, I will give you a separate note where I will where basically I have derived how to use this. Basically I have derived this solution that comes from using this biharmonic equation. Okay, but at this point of time, and in the interest of this class, we will just say that, okay, if the stream function satisfies this biharmonic equation, our solution to this equation is a known form, which is basically something like this, where these qn's are nothing but the Gegenberg polynomial. Okay, for instance, so you can see that once you know the Legendre polynomials at each and every order, if you integrate this from -1 to eta, you will get the Gegenberg polynomial. For example, I just show that, can you tell me what is P1 of eta? So what is the first Legendre polynomial? Can you tell me? Do you remember? Do you remember the first Legendre polynomial? So I'll just tell you, the first Legendre polynomial is cos theta, which means as a function of eta, it is just eta. Okay, because eta is cos theta in our transformed coordinate system. Okay, which means Q1 of eta, that is the first Gegenberg polynomial, is nothing but -1 to eta P1 of eta, which means it's eta times d eta. Okay. I hope this is clear. So can you tell me what this integration would basically be? Can you tell me? That's a simple integration, right? You are just integrating eta d eta from -1 to eta. So what would this be? So this would be eta squared by 2, and this will vary from -1 to eta. Okay, which means it would be what? It would be just half of eta squared minus 1. This is q1 of eta. In the same way, can you tell me what is this? d eta of qn of eta. What would this be?
Eta.
Yeah, so it's eta for n equal to 1. So in general, it would just be the Legendre polynomials, right?
Yeah.
Okay, so these things that you need to understand, and you can search in the net the Gegenberg polynomials, what the Gegenberg polynomials look like. But yeah, so this is the relationship between the Gegenberg polynomial and the like Legendre polynomials. Okay, all right. So this means that if I know the solution of psi looks something like this, then all I need to do is I just need to evaluate the unknowns ans, bns, cns, and dns. Okay, so can you tell me, is it just sufficient to calculate the an, bn, cns, and dns, or there is something else that we also need to know? Okay, did you get my question? So what I said is that since I know the form of solution of psi, see what we need. All we need is just the psi, because if we know psi, then we know its velocity, and if we know velocity, we can eventually calculate the drag force. Okay, so this means that if I know psi, everything else is known. So our sole objective is basically, so the objective is basically to evaluate this psi. And we already said that the psi has basically this form, because psi satisfies this biharmonic equation. So in essence, what we need is, we just need to evaluate these constants ans, bn, cn, and dn. Okay, I'm asking that, is it just, so the thing is it just that we need to just evaluate these ans, bns, cns, and dns, or there is something else, or there is one more thing that we also need to evaluate? Can you tell me, like, can you give some hint on that? See, the answer is not so trivial. You just need to look at this series solution, and you just need to think that how does a series solution behave basically. See, the thing is, see, this is an infinite series, right? So we cannot just go on and evaluate all the individual terms. That is, we cannot just evaluate n equal to 1, n equal to 3, up to how many terms we need. Okay, so we also need a constraint which will say that, okay, now my series will be truncated up to a certain point. Okay, so in other words, I also need that what modes, so these are basically known as modes. So what modes of n will be responsible for as a part of my solution. Okay, and these modes is reflected from the far field boundary condition. Okay, so the idea is we will first use as a part of the solution procedure, we will first use the far field boundary condition into evaluating the number of modes that we need and also the constants ans and bns. Okay, so three things can be obtained from the far field boundary condition. One, the modes that are responsible for the solution of psi, then these ans, and then these bns. And then using the boundary condition on the surface of the sphere, okay, we will evaluate the other constant, that is cns and dns. Okay, that's the idea, because qn is already known. So at each and every modes, that is at n equal to 1, n equal to 2, the Legendre polynomials are known, which means that if I integrate those Legendre polynomials, I know the Gegenberg polynomials. Okay, so that's basically the idea. All right, so we'll start off this problem. We will start off this problem. So as I have said, we will know the number of modes that are responsible for the solution of psi, and the fact that how this ans and bns would look like, we need to use the boundary condition. So we need to use the far field condition. So all we know is that the far field velocity, so this is the, so I would say this is the step one of the problem. Okay, that is the step one is using the far field conditions. So I know that the far field velocity with respect to an axis, okay, that is fixed at the sphere center, the far field velocity looks something like this. So it is 1 minus rho squared minus u times Ez. Okay, which means that I now have just uz. Okay, so uz infinity is nothing but 1 minus u minus rho squared. Okay, but we are solving this in what? So we are solving this in a system which just varies, in r, eta, and phi. Okay, we don't have phi because it's a axisymmetric problem, which means I need to convert this velocity into an u r infinity and u eta infinity or u theta infinity, whatever you wish to write. So based on this, we will use the fact that we will use how the velocity is transformed in a spherical coordinate system. So as you can see, if so, this is the uz that we have. So if we want to write uz in terms of ur, then uz is, so ur is nothing but uz times eta, or the other way around. We just want to write ur in terms of uz because uz is known to us. Okay, that is uz infinity at far field is known, which I have just now written. This means that ur infinity would be just uz infinity times cos theta. Okay, and that you can basically have from this. So this is basically the spherical radius, as you can see. So ur, which is the radius, which is the spherical radius velocity, or which is the velocity associated with the spherical radius, is basically this ur. U theta would be in this direction because the sense of theta is basically is here, which means that minus u theta will be along this direction, and that's why u theta is nothing but minus uz sine theta. So this is just trigonometry. Okay, so based on this, what we will do is we will just evaluate ur infinity, which is nothing but uz infinity times cos theta. So uz is what? So uz is just this. So uz is just this, which means it is just 1 minus of u minus rho squared, okay, times eta. Now this rho is a cylindrical radius, right? So we need to convert the cylindrical radius into spherical radius. So can you tell me what is the relationship between the cylindrical radius and the spherical radius? So what is the relationship between rho and r? Can you tell me? By looking into this system. So rho is what? What is rho in terms of r and eta?
R sin theta.
Yeah,
R.
exactly. So yeah, exactly. R sin theta, it is r times square root of 1 minus eta square, because sin theta is just square root of 1 minus eta square.
Yeah.
Okay. Which means the rho square would be just r square times 1 minus eta square. Okay. And then this is again multiplied with this eta. So this means that this ur infinity is nothing but, I'll just write it here once again. So this u r infinity is nothing but 1 minus u minus r squared times 1 minus eta squared, okay, multiplied by eta. So this is u r infinity. Again, I would repeat that this u, this is unknown. So this is a priori unknown, as I have said. So this is a priori unknown. And this can be obtained. So this is the final task. So our final task is to obtain this u by enforcing that the net force on the sphere is 0, as I have already said. So if an object have a net force which is 0, then the object have two options: either it will be at rest or it will move with a constant velocity, basically. And that constant velocity is, so at rest we are not interested because that's a trivial solution. So our interest is to evaluate the velocity with which that object would basically move, okay, in the creeping flow limit, of course. And this would be obtained later on by using the fact that the net force on the sphere is 0. Okay. So now this is u r infinity. Okay. Similarly, you can say that u theta or u eta, whatever you write, infinity is nothing but, so u theta infinity is nothing but minus u z infinity times sine theta, which means it is times 1 minus of eta squared. So if I just substitute the value of u z infinity, this would become what? This would become u theta infinity, which is equal to minus 1 minus u, okay, it's 1 minus u minus r squared times 1 minus of eta squared, okay, oops, just be that, sorry. So it would be, so what it would be? It would be r squared times 1 minus of eta squared, okay, multiplied by square root of 1 minus eta squared. All right, so this is u theta infinity. Okay, so from the far field condition, from the far field boundary conditions, I know what is u r infinity and what is u theta infinity. So with this, can you suggest that how do I obtain the stream function as far field? Because I said that the far field stream function would dictate what modes will be present in this equation and the constants a n's and b n's. So is there a relation that you think that you can think of that? So indeed we have a relation, right? Because we know that in spherical coordinates, u theta infinity in terms of the stream function approach or in terms of the stream function looks something like this. So it is 1 by square root of 1 minus eta squared, okay, into 1 by r into del psi infinity by del r. Okay, so this is the definition of u theta infinity in terms of the stream function. So this is very similar to the Cartesian. So this is very similar to the Cartesian coordinates, except that now my system is a spherical system that we are looking for. Okay. So this relation is available in the internet, or it's available in any standard book of fluid mechanics. Okay. So what now we'll do is we'll just substitute this in here and try to integrate it to evaluate this psi infinity. And let's see what we get. So if I just substitute it in 2, we'll get minus 1 by square root of 1 minus eta squared. Okay. Times 1 by r into del psi infinity by del r, and this would be what? This would be minus 1 minus of u minus r square into 1 minus eta squared, okay, multiplied by, so this is multiplied by square root of 1 minus eta squared. Okay, again I would say the objective is to evaluate this psi infinity. All right, so this, let's simplify this. So this would be this would get cancelled. So this means if I just want to evaluate del psi infinity by del r, okay, this equation would be something like this. So it would be 1 minus u times r minus r squared. I think this would be what? This should be r cube, basically. This would be r cube. Okay, times 1 minus eta squared. Okay, and this is then multiplied with 1 minus eta squared. It's just that I'm just bringing these two quantities into the other side of the equation. Okay. So now let's integrate this. So what now is that we will integrate with respect to r. So if we do this, what do we get? We get the psi infinity as a function of r and eta as what? So it is 1 minus u into r squared by 2 minus, it would be r to the power 4 by 4, okay, into 1 minus eta squared, and then this would be 1 minus eta squared. So is it all, or we are missing some terms here? Can you tell me? Is this all?
One constant.
Yeah, exactly. Is it a constant, or is it just a constant or just some function?
Function of eta.
Yeah, exactly. So since you are integrating with respect to r, so this would be just a function of eta. Okay. Now, all right. So you can tell that. Just 1 second. Yeah. So you can tell that without any loss of generality by, see, we have evaluated the stream function from the definition of u theta, okay? From the definition of u theta. You can also evaluate the stream function from the definition of ur, right? So stream function is related to the two velocities, right? So you can evaluate it either from ur or you can evaluate it either from u theta. If you do that, you can, and if you compare that, you can say that without any loss of generality, this function of eta at r tends to infinity, this would basically be equal to 0. Okay. I have not shown this explicitly, but you can eventually show that this function of eta has to be equal to 0 at r tending to infinity. Okay, which means that psi infinity as a function of r comma eta is basically something like this. Yeah, so what does this become? So it just becomes, 1 minus u, okay, into r square by 2, okay, and let's simplify. So what do we get? 1 minus into r square by 2. Okay, and then I'm just thinking of a simplified form of writing this. Okay, let's just write it something like this. So it becomes 1 minus u into r squared by 2 plus r power 4 by 4 into 1 minus eta square ka whole square. Okay. This means that psi infinity as a function of r comma eta is basically 1 minus u into r squared by 2 plus, this would be r power 4. So this is fine, right? Did I make any mistake? Oh, there should be a minus here. There should be a minus, right? It is this multiplied by this. So there has to be a minus here. Okay. And there has to be a minus here. This becomes r squared by 4 into, if I just break this, so it would be what? It would be 1 minus 2 eta squared plus eta power 4. Okay. All right. So if I now just write this, if I now just simplify this, it is eta infinity as a function of this. Okay, into 1 minus u into r squared by 2 minus r power 4 by 4, okay, plus r power 4 by 2 eta squared, okay. Right, this is fine. I hope this is
1
fine.
minus 1 minus eta square should be multiplied with first term.
Okay, yes. So yeah, exactly. That's correct. So this term, so there should also be multiplied by 1 minus eta squared. Okay, good. Thank you. So this should be also multiplied by 1 minus eta squared. Yeah. Okay. Then this term would be plus of this, and then this term would be minus what? R power 4 by 4 into eta power 4. Okay. So if I now just simplify, so idea is that I want to segregate all the terms so that we would just know that what forms, what modes of the far field velocity would be present in a generalized solution. Okay, so this is this. So this would be what it would be. Yeah, it would be something like this. It's 1 minus u into r squared by 2. Okay. Then what we have is minus 1 minus u. If I do this, minus 1 minus u into r squared by 2 eta squared. Okay. Just that I'm just breaking this term. Okay, in this term, I'm just doing that. And then the other terms would be what? So other terms would be minus r power 4 by 4. This term would be there. Plus r power 4 by 2 eta square minus r power 4 by 4 eta power 4. Okay, I think that's all. That's the terms that that will be there. So what I will now do is I will just write this psi infinity as something like this. So just have a look and let me know. So psi infinity can be written as 1 minus u into r squared by 2 minus r power 4 by 4. Okay. Plus this can be written as eta power 0 because eta power 0 is nothing but 1. I'm just forcefully writing it as eta power 0. Plus I can write this as r power 4 by 2 r squared, okay, minus 1 minus u into r squared by 2 times of eta squared minus r power 4 by 4 r squared into eta power 4. So the logic is that I am just writing these terms as a function of r multiplied by a function of eta. So if I do that, so I'm just rearranging these terms as just like this. Okay, so I have an eta power 0, I have an eta squared, and I have an eta power 4. Okay. So then again, why are you doing this? So the objective is that I again want to write this expression as something like this. So I want to write this as some function of r. So the idea is that I want to write this as a function of the Gegenberg, as a function of r times the function of the Gegenberg polynomials. Okay, I want to write it as some function of f1 of r times q1 of r. Okay, plus f2 of r times of q2 of r plus f3 of r times q3 of r plus, let's say I have f4 of r times q4 of r plus the higher order modes. Okay, then if I since these are just sorry I just made sense. So this is the function of eta. Okay, these are not function of r. So the f functions are just function of r. These are some function of eta that we know. All right, so the idea is that if I can so what I am trying to do is that I am trying to write this form into this form. Okay, this means that I just need to evaluate this f1, f2, f3, and f4. Okay, so such that I can write it in the form of these Gegenberg polynomials. Now, why do I want to write this in the form of Gegenberg polynomials? That's because the solution of psi, the series solution of psi, is in terms of a Gegenberg polynomial, right? It's here, as you can see. So the series solution of psi is in terms of this Qn. So if I can write my entire form as a series solution of these Qn's, okay, then I can find out what these constants an, bn, and cn and dn would look like. So that's the broad idea. Okay, so we will stop here for today. The idea is in the next class we'll begin from this point. We will begin from this point. Okay, we'll begin from here and try to evaluate what these f1s, f2, f3, and f4 would be, and then how many modes. So this I have written it as a series solution, but we will see that only n equal to 1 and 3 mode will survive and all other modes will not be present. Okay, so we will see that, and then we'll proceed to calculate what will be the velocity of the sphere when it is subjected to that background flow. Okay, ultimately we'll evaluate that unknown u that we are trying to solve for. uh, we'll we'll stop here for today. We'll begin from this step in the next class, and then once this is finished we will stop creeping flow, and then we'll move into the boundary layer theory and finally conclude. We have just 4 or 5 sessions left. we'll in one class, I mean in the next class we will try, in the next class or in the next to next class, we will try to solve some boundary layer. We'll try to solve some problems on the boundary layer, because this is important. This topic is very much important with respect to your exams, or with respect to the assignments as well. And then we will solve, or we will see something, we'll see a new topic which is known as hydrodynamic stability. And once that is done, we will try to cover some basics of turbulence, and then that's the finishing things that we will do. So turbulence is the last part of this course, and I think that's it. That's the agenda basically. So in the next class, as I have repeated, we'll take it from this step. We will try to evaluate this F1, F2, F3, and F4, and also the fact that how many up to which value of n should we truncate the series. And then once that is known, we will evaluate the constants, the other two constants, Cns and Dns, from the boundaries from so this can be obtained from the boundary conditions on the sphere surface. And then we will ultimately evaluate the unknown velocity u that we are trying to solve for. Okay, so we'll stop here for today. If you have any doubts, you can ask, or we'll meet in the next class. Thank you.
One doubt only.
Yeah, go on.
In this equation, in denominator capital R, how is it coming? I don't get.
Yeah. Capital R nahi aayega actually. Yes. So this capital R is actually 1. So I wrote it as a capital R in my notes. Sorry for that. Yeah, capital R nahi aayega. See, this capital R is basically, yeah.
That
So
1
this,
minus
yeah,
R square. Yeah,
yeah.
okay.
This is the capital R. We took it as 1, okay, for the sake of simplicity.
Okay,
Okay.
okay.
So yeah, I understand the math is little bit complicated here, but once you get the final result of this, you will appreciate that this problem we are actually solving it analytically. It's a very difficult problem to solve analytically, but because of the fact that we can use stream function, we can try to solve this analytically, and we will ultimately we will see that what's the velocity with which the sphere would move, and we will see some special cases of this solution as well. This we are doing through all these steps that we are doing. This is just the math, okay, and we will appreciate the physics as well once we get into like the final stages of the problem. Okay, so we'll meet in the next week. Thank you for attending this week's session. If you have, yeah, I will try to contact with the instructor uh, on the queries, on basically on these queries, basically on this, okay, as well as the second question of the assignment 7, and then whatever he says, I'll post it in the discussion forum of the group. Thank you very much. We'll meet in the next week. If you don't have any doubts, I will end this meeting. Yeah, that's it.
Okay, thank you.
Yeah, sure. Thank you.